Hi guys, Mr. Rocco here. Hope you had a good weekend. We're going to keep moving on with astronomy. My goal is to finish astronomy before we break for the holiday break in a few weeks. So we have a few more topics to cover in astronomy. I'm going to start with evidence for the Earth's rotation. So this video will be about two things. Two pieces of evidence to prove that the Earth rotates. One is called the Coriolis effect, and the other is the Foucault pendulum. So let me get right into the Coriolis effect. This is the definition. Any object traveling along the surface of the Earth will appear to bend or to deflect or to curve to the right in the northern hemisphere, and any object traveling along the surface will appear to bend or deflect to the left, right in the north, and appear to deflect or bend to the left in the southern hemisphere. And let me pull up this YouTube video, so we're going to watch this for a minute.
Hey, Australian people, have you ever been in the Northern Hemisphere? Have you ever noticed whether your toilet drains differently than it does here? No? You heard maybe it has something to do with the Coriolis effect? Welcome to another edition of I Don't Think It Means What You Think It Means. You probably don't spend a lot of time thinking about how water drains from your toilet, but somehow the idea that water drains differently in the northern and southern hemispheres has made its way into our collective consciousness. Furthermore, the reason for this phenomenon has been pinned to the Coriolis effect, which refers to the way the Earth's constant eastward rotation influences how we view the trajectory of certain moving objects. Because the diameter of the Earth at the equator at 40,076 kilometers is so much greater than it is at the poles at 0 kilometers, the land of the equator is moving lots faster than the land everywhere else, about 1,638 kilometers per hour at the equator compared to about half that at 60 degrees north latitude and pretty much stationary at the poles. And yes, the Coriolis effect, named for 19th century mathematician Gustav Coriolis, does indeed influence objects traveling across the face of the Earth due to this constant eastward rotation. If you tried to throw a baseball from the equator up to your friend standing at the North Pole, your ball would appear to veer to the right because it would maintain the greater momentum of the place it started from. On the other hand, if you were throwing the ball to the South Pole from the equator, the ball would appear to veer to the left for the same reason. So although the Coriolis effect is totally a thing, the application of this principle to draining water in Earth's two hemispheres is just bunk. Our planet spinning around once every 24 hours isn't a big enough deal to affect a toilet that takes 5 seconds to flush. Basically, the direction water drains is dictated by the shape of the basin it's in, the sink or toilet bowl or whatever. The Coriolis effect does, however, influence bigger, slower-moving fluids, global air and ocean currents, for instance, which can end up giving hurricanes their spin. If the Earth didn't rotate on its axis, among the very many and unpleasant things that would be different, one of them would be that winds wouldn't blow either west or east. They'd flow from the poles, which are naturally high-pressure areas, to the equator, where there's low pressure, and back again. But the Coriolis effect deflects these winds to the right in the northern hemisphere, to the left in the southern hemisphere, which creates weather systems that rotate clockwise in the northern hemisphere and counterclockwise in the south. The Coriolis effect, working at that scale, does affect entire climate patterns, but it can't make itself felt on whatever you left in your toilet. Sorry. The Coriolis effect. Weather, not toilets. Got it? Good. Thank you for watching this episode of I Don't Think It Means What You Think It Means. If you have any questions, comments, or suggestions for us, you can find us on Facebook, Twitter, or of course in the comments below. And if you want to continue getting smarter with us here at SciShow, you can go to youtube.com/SciShow and subscribe.
Okay. So it does deflect certain things. Let me show you this animation here. All right, so if you look at this top picture here, let's say you have a plane. A plane's going to fly from Anchorage, Alaska, which would be way up here. It's going to fly toward Florida, which is down here. As the plane is in the air, right, the plane leaves Anchorage, Alaska, starts to head in a straight line toward Florida. While it's flying, the Earth, remember, is rotating to the east, to the right in this picture, which means you're going to miss your target to the right. So let me hit play and you'll see that. So you're starting, it's up here, your target's over here. The plane takes off. While the plane's in the air, notice you missed the intention. The path you wanted to travel was the dotted line. You're heading to Florida, but your path ended up curving to the right, which you might say, well, that looks like to the left of that dot. It is to the left of the dot, but remember, you're standing, you have to put yourself back at the starting point. So if you're standing at Anchorage looking toward Florida, that is to the right. I call that the stage effect, right? If you're, let's say you're in the audience and you're looking at someone on the stage, if they walk to their right, it looks like it went to the audience's left. So same idea, I call it stage effect. So anyway, this missed to the right in the northern hemisphere. Now, did the plane actually veer to the right? No. It's just while the plane was in the air for so many hours heading to Florida, the Earth is rotating. Again, this is proof that the Earth rotates. Let's go to this bottom picture. So now we're in the southern hemisphere, which if you recall, it's going to be the opposite. It's going to veer to the left. So here a plane is going to leave Tierra del Fuego, Argentina, which is in southern South America. It's going to start to head north toward Rio de Janeiro. It's going to miss its target to the left because, again, the Earth keeps rotating to the east. So let me hit play and you'll see that. And there you can see what happened. So the plane wanted to go this way toward Rio, but as it was in the air again for those few hours, it appeared to curve to the left and it missed its target. So that is a thing, totally a thing, called the Coriolis effect. It doesn't affect everything, but it does affect some things. This would show, this is kind of a top view. So you're looking down on the Earth. This would be the North Pole right here in the center. So let's say, you know, you're launching a rocket toward the equator. This, if you're looking down on the Earth, the outer edge of this circle would be the equator. So this is equator here. And you're standing at the North Pole right here. You're going to launch a rocket toward this target right here. And while you're doing that, the Earth is rotating. So the Earth is going to go west to east. So if you can see, this is North America here, west coast, east coast. So the Earth rotates counterclockwise. See these arrows? So if you launch the rocket, let's say you're launching the rocket, right? The Earth is rotating. Your target ends, your deflection, ends up to the right. You were going for this, but you ended up hitting over here to the right because the Earth turned while you were launching the rocket. And that's going to be that special number. So for every hour that the missile, let's say a rocket's in the air, it's 15 degrees per hour. The military has to take that into account. So if a military, let's say you have an aircraft carrier out in the ocean and they're going to shoot a missile at a country, they have to take Coriolis into effect for every hour that the missile's in the air. So if the missile was going to be in the air for 2 hours and they're trying to hit a certain target, well, 2 times 15 is 30. So they should launch that missile but shoot 30 degrees to the left, right? Because this way, when the target is rotating around, it's going to be in the spot that it wants them to be there. Another analogy I give, sometimes I do this in class, I think of football. If you think of football, let's say you have your quarterback and then you have a wide receiver. And let's say the wide receiver is going to run up the field, 15, 20 yards, and then do a straight cut across the field. Well, when you go to throw the football, right, do you throw it right at where the wide receiver is at that instant? No, you do what they call lead the wide receiver. You might throw it several feet out in front of the wide receiver so that by the time the ball gets from you to the wide receiver, he is in that right spot. So that's leading the wide receiver. So I think of it that way as well. So Coriolis will affect these things: winds, long-range winds, the planetary wind belts, which we haven't done yet when we get into weather. So we have what's called the jet stream. You might have heard of that. That affects winds. So in the United States, everything tends to go from the northwest from the southwest toward the northeast. And that's because of the Coriolis effect. In other parts of the world, it does the complete opposite. Instead of going from west to east, the winds will actually go from east to west. They'll go complete opposite. And again, that's because of Coriolis. long-range missiles, so missiles that might take an hour, 2 hours, 3 hours to reach their destination. They have to take Coriolis into effect. Ocean currents, which are affected by the winds. I'll show you a map in a minute. And storms, as the guy was talking about in that YouTube clip. In the northern hemisphere, a storm is a low pressure tornado, hurricanes. The winds around a tornado and a hurricane in the northern hemisphere circle around counterclockwise. But if you're in Australia, in the southern hemisphere, the winds around a low pressure actually go the opposite way. So it depends on which hemisphere, will depend on the direction that the winds will spiral in something, let's say, like a hurricane. This was a question on a Regents from several years ago, so a very easy question. Earth's planetary winds, and once they started talking about curve to the right in the north due to the, and the students had to know, oh, we're talking about the Coriolis effect. So 1 was the correct answer. Doppler effect is, we talked about that with the red shift. That's when a siren is coming toward you and it gets louder, and then it passes you and it gets softer, right? Winds curving has nothing to do with the tilt. That's seasons, which we'll talk about in the next video. And gravity obviously isn't going to affect the way the winds curve. This is in your reference table on page 4. This is the ocean current map. And you have 2 types of ocean currents. You have warm water and cold water. If it's a black arrow, it's warm water. If it's a white arrow, it's cold water, which is going to then affect your climate, right? If you have warm water circulating next to the coast of your country, that's going to keep your temperatures along the coast obviously warmer. And the opposite, if you had cold water circulating next to the coast of your country, that's going to keep your temperatures cooler. The United States is a perfect good example of that. On the East Coast, our side of North America over here, we have what's called the Gulf Stream, which is a warm ocean current. It takes warm water out of the equator down by the hotter parts of the world, and it pumps it north, and then notice it curves which way? To the right. So it comes up, let me reset this. It kind of comes up like this, and then as it turns, right, it makes that right-hand turn. There's the Coriolis effect, curving to the right. And it brings all that warm water along the East Coast, right, which is what hurricanes thrive on. So when a hurricane comes up the eastern seaboard, as long as it stays in that warm Gulf Stream, that's what keeps it, strong. Now, if you go out to California, and I've never been personally, but some of you probably have, you have a different situation. You have a cold ocean current. It's called the California current. That takes water out of Alaska, up here in Alaska Bay, which is cold water coming from Alaska, pumps it south, brings it down the west coast. It's also curving to the right, which you might say, well, Mr. Rocco, you don't know your left from your right. Remember, you're looking in the direction where it's coming from. So you have to be standing up here in Alaska Bay, watching the ocean current, the California, go away from you and head south. So that is like, again, the stage effect. That anytime it comes from the north, right looks like left. So when it comes from the north and heads south, it looks like it's going the opposite way it really is. So it is curving to the right. That isn't to the left. But it's cold water. So if you've ever been out to California, and I have plenty of kids over the years say, yeah, I've been out to California. I said, what's the water like over there? It's not Florida water, right? Florida water, it might be in the 80s or 90-degree temperature water, nice, warm, tropical water. You don't have that in California and along the west coast here, Oregon and Washington. You're going to have water in probably in the 60s. Maybe it might get to 70, but that's about it. You have much cooler water over here. That's a cold current. But you can see, again, that's to the right, that's to the right. Now, if I go down here to South America, same situation. You have the Brazil current on the eastern side of South America and the Peru current on the western side. And they have the same thing. They have a warm current on the east coast and a cold current on the west coast. So it's pretty much mirror image to North America. We both have west coast with cold water, and we both have east coast with warm water, except they flow differently. In this case, the Brazil current heads south, the Peru current heads north. But Coriolis, again, everything flips. So now you're curving to the left. But again, left looks like right when you're looking at the Brazil current. So it's bringing warm tropical water again from the equator. It starts to flow south, and then it goes along the coast and then turns to the left. Again, you might say it looks like right, but it's not. That's to the left. Then the Peru current is taking cold water from down here by the South Pole, and it starts to flow north, goes along the coast of South America, and brings that cold water, and you can easily see the left-hand turn right there. So that's curving to the left. And then one more I want to point out to you is over here. If you ever see the movie Finding Nemo, right, classic Disney movie, Pixar, they talk about the EAC. Let me clear this. This is the EAC right here. I'll circle it. So when the scene where, the turtles are flowing through the current and Nemo's father's on the back of the turtle and they're heading towards Sydney, Australia. Well, Sydney, Australia is actually down here. I'll put an X. It's in the southeast corner of Australia. That would be where Sydney, Australia is. So the turtles are up here, a little further up on the coast. It's the EAC is carrying the father there, Marlin, I think his name is, and carrying him south along that EAC down to Sydney so he can find Nemo. So Pixar did try to use some actual science in the movie, which I always appreciate as an earth science teacher. They put some real science in there that they're following the EAC and the turtles are heading towards Sydney. But that is a warm ocean current, so it's going to bring warm water to Sydney. And then again, notice when it's coming from the north, it's going to curve left. You see how it has that left hook right there, but left looks like right, but that is to the left. So it's always left in the southern hemisphere and right in the northern hemisphere. Coriolis. Toilets, and the guy talked about that in the video. Toilets have no effect. They sometimes put in a movie, they'll say, well, the way the toilet flushes in New York is different than South America. The toilets flow the other way. They flush backwards. No, has nothing to do with that because it takes 2 seconds for a toilet to flush. We're talking about long-term things like ocean currents and things, long-range missiles. It really is affected by how they build the basin, like the guy's talking about. The shape of the toilet. Also, inside the toilet, if you lift the lid of the toilet, on the inside underneath in the rim there where the water flows out, manufacturers will point the little jets in different directions. So it might depend on if you have an American Standard toilet or a Kohler toilet. Different manufacturers will manufacture the jets differently sometimes, and you might have 2 different toilets in your house, and you could just prove that. Flush one toilet, the water might go clockwise. Flush another toilet, it might go counterclockwise. You might even have a toilet where the water flows straight in, like goes straight down, not even in a circle. So it depends on the manufacturer. So it has nothing to do with the Coriolis effect. All right, the other clue besides the Coriolis, again, these are to prove the Earth rotates. It's called the Foucault pendulum, which is when they say freely swinging means will continue to swing for as long as the length of the wire or rope or whatever and the weight that's attached to the bottom, as long as that is going to allow. Will it go forever? No. But freely swinging means nothing is really affecting it, causing it to turn in any other direction. So anyway, a freely swinging pendulum will appear, and I stress that word again, appear to change direction, but it's actually not changing its direction. The earth and the floor underneath the pendulum is actually rotating. And you can actually go to the museums. I'll show you some pictures, and I have a couple of videos here of these pendulums. They're really cool to see. This goes back to the 1800s. 1851, a gentleman named Jean Foucault, and that's why it's named the Foucault pendulum. He took a 67-meter, 28-kilogram pendulum, which if you convert that, I put the numbers down here. So that was a 219-foot wire and a 62-pound sphere at the bottom attached to the wire, and he created a pendulum in a very famous building in Paris, France, called the Pantheon. And what appeared to happen was because from the north, let's say this is the Earth, right? And this is the North Pole in the middle. And as I showed you in that previous slide, the Earth appears to go counterclockwise. So in the north, when you're looking down on the Earth, it appears counter. The pendulum is going to appear to rotate the opposite way. The pendulum is going to go this way, clockwise. And so it says, with respect to the Earth, it's slowly rotated clockwise. All right. And this is actually a picture of the Pantheon building. So up here in the top of the dome, he hung a 219-foot wire straight down to the lobby with a 62-pound sphere at the bottom. And that was the building that he did this experiment. This is the Pantheon, I believe, in Paris, and you can go visit that. It's a very famous attraction, and you can actually see this pendulum. And again, if you go to some museums, you'll see that in there. It has the hours of the day here, so you got your 24-hour day. And what is going to happen is this pendulum is going to continue to swing in a straight path back and forth, the floor and the whole building being attached to the earth is going to rotate. So this thing will rotate, but the pendulum will appear to turn. It's not really turning, and that's what makes it freely swinging. It's just attached at one particular point way up at the top of the ceiling, and that's what makes it freely swinging. This is another pendulum you might see if you go to Spain. This is in one of the museums over there. And they set up these pegs, which is really cool. So what will happen is it'll knock this peg down here, and then way on the opposite side of the circle, it'll knock the opposite one. And this will continue to go clockwise like this, right? Spain is in the northern hemisphere. So pendulums in the northern hemisphere appear to go in a clockwise direction. If you're in Australia, right, so it would go the opposite way. The southern hemisphere would go counter. So anyway, it's going to knock this pendulum down next, and then the one over here, and then the next one. It's going to keep knocking these little, knocking these pegs down, I should say, one at a time. This is another one if you go out to Boston. This one I did visit, so if you go to the Boston Museum of Science, you'll see this in the lobby. It's a Foucault pendulum. So you'll find a lot of your museums have these Foucault pendulums set up, and they will just slowly swing back and forth, with the whole floor rotating over a period of a day and appearing to change direction. Again, the pendulum's not changing, right? The pendulum, let me stress that. It appears to change. It's the floor that's turning because it's attached to the earth, and the earth is rotating. This was a picture, or actually a question with a picture on a Regents from a few years ago. So it says, the photograph below shows a Foucault pendulum at a museum. The pendulum knocks over pins in a regular pattern as it swings back and forth. This pendulum movement and the pattern of the pins is evidence for what? And again, this is to prove the earth rotates. So it has nothing to do with the shape of the earth, has nothing to do with the gravity to the sun, has nothing to do with that we're nearly circular, but I'm going to go with 3. Oops, that's a horrible line, Mr. Rocco. So it's hard to do with a mouse, so I'm going to circle like that. There we go. So it has to do with the rotation on our axis. Now with these pendulums, sometimes they'll give questions like this. I put this here. They'll have the pendulum might be here, and it's swinging back and forth like this. They'll say, what's the pattern? They might even have you finish the pattern. So when it starts swinging, right, they push the pendulum, it's going to knock down in a clockwise direction. It's going to knock this one and this one, and then you're just going to keep going one peg at a time. It's going to knock down this one and then this one. So I'll number them. This would be the first set of pins, 1 and 1, and then 2 and 2. And it's going to keep going. This would be 3 along with 3. Right, so you're just going to keep moving. They might give you a multiple choice question. Say, what's the next? They might do that. Put 3 pins down on opposite sides and say, what are the next 2 pins to get knocked down? And they'll have 4 diagrams, and the student has to pick the correct one. So, let's say they did another diagram, right? This would be the 4th pin, and this would be the 4th pin. So they might say, that's the correct answer. Circle the 2 pins that get knocked down, or something like that on a Regents. So look for questions like that on a test. Here's another one from June 17. Diagram shows, again, changing path of a Foucault pendulum. It's attached up at the ceiling, so that's what makes it freely swinging. And then you see after 0 hours, when it first started, it was here. 2 hours, again, it's going clockwise, so it was here and here. 4 hours here and here. 6 hours here, 8 hours, etc. So it keeps rotating in that clockwise direction. And then it just says, this apparent change in direction is evidence, again, that the Earth is rotating or turning. So in this case, they didn't use the word rotation, but they gave a definition of rotate, right? Turns on its axis. So I'd go with choice 4 on that one. Then I have a couple of short videos here. Let me pull this one up. Oh, this is animation, sorry. Takes a minute to load. All right, so what you're looking at here now, this is in New South Wales, which is in the southern hemisphere. You're down in Australia. And so what you're seeing here is a pendulum coming at you in this left picture. So they set up a camera. The pendulum's coming at you. And back here is a set of stairs and there's a wire. You can see the wire attached to the pendulum. So over here is the animation that matches the actual live camera. And so this green line is the wire attached to the pendulum. That red line is just a line in the back there on the stairs as a reference line. So when they first push the pendulum, okay, you see how the red line and the green line are in sync with one another. They're coming directly at you. So the green and red line are together, right? You just initially pushed the pendulum. Then you'll see, and you go to the next picture down, it says about an hour later, the amplitude has diminished, meaning it's changed direction. But again, did the pendulum change? No, it's that the floor rotated. And so now the pendulum, even though it's still going in the same direction, appears, you notice the green line isn't in sync with the red line like it was up here. It's now cutting across it. It looks like it's going left to right with reference to that red line. But again, it's not that the stairs, that the pendulum changed direction. The actual stairs, the whole floor, everything in there moved except for the weight of the pendulum. There's a law called the law of inertia. Law of inertia says an object at rest stays at rest, an object in motion tends to stay in motion. So law of inertia is going to keep the pendulum going in the same back and forth swing direction, but it appears to now cross the path of the red line, different than the first picture here, because of the fact that the Earth rotated. And so that's what that shows there. And I think I have one more video. This one, yeah. This is I found a lady videotape. This was at the Chicago Museum. I'm not going to show the whole thing. I'm going to fast forward to, what did it say, 6-minute mark? Yeah, 6 minutes. So you can see the pegs get knocked down.
I'm still waiting, getting closer. One or two me. It's gotta be now. Ah! Not yet. Come on. Oh, so close. I wonder if it'll go over all at once. I know, it's so suspenseful. I think the next swing, I think it moved it a little. You see, it's nudging it. Oh! Whoa! Oh! Not yet, but soon. Whoa! Got it!
Okay, you can see she was very excited to see the pendulum knock that peg down. But anyway, you get the idea behind the Foucault pendulum, and I think that's it. All right, this will get posted on Canvas. Watch the whole video in its entirety. Go back, rewind if something doesn't make sense. Also, please recall, I put the notes on Canvas as well. So you have the video to watch where I explain the notes, and then you also have the actual notes. They're listed on each week, right above where the video is. So if you click on the link above the video, it'll say evidence first rotation or something like that. That's the actual notes. So you always have those to refer to when you're doing when you're doing the homework assignments. So you could always go back and watch the video and or look at the notes, and that will help you as well with the assignments. Okay, hope all is well, and I will talk to you soon. Bye.